5. So this means that from the perspective of topology, this is actually a 4G minus 5 dimensional space. So all this stuff here vanishes, and this is due to. And also, I mean, I should say that this unstable cohomology, to prove that this actually stabilizes, is the work of many people among Madsen, Weiss, and also the explicit form of the stable cohomology is known as Mumford's conjecture. And it has been also proven by many people that the actual form of this stabilization, so that this Morita and also Galacious, many people, and also this modular space of curves, I also want to say it's also very relevant for string and for in this topology also is relevant. All right, so we have this stabilization, and then in the middle between this stable cohomology and this virtual cohomological dimension, there's the interesting part and very little is known about this. So this is the unstable cohomology. And yeah, so this is what I'm going to talk about today. This is where the motivation comes. And the main sort of idea that I'm going to talk about here is that you can make estimates on the amount of cohomology that is in here by looking at the Euler characteristic of these kind of spaces. So let's now Euler characteristic. This is a computation by Hara and Sergi. X6. And so what to do, you compute the Euler characteristic of this space, MG, and you know that it's just the alternating sum over the dimension. You can express it as the alternating sum over the dimensions of the Betti number which are the dimensions of these cohomology groups. And Hara and Sergi, they proved that for large G, this alternating sum is first of all, it's alternating itself, and it's behaving like some constant and a factorial and some exponential function. So there's some exponential, there's a factorial, and there's an alternating sign. And this tells you already quite some things. So first of all, you can immediately deduce from this that the dimension, the total dimension of the cohomology, it grows super exponentially. So in fact, there's the following behavior. It grows more than c times g to the power of 2g. So the g to the power of 2g comes from this factorial. And then you can just choose, you can always find some constant c in the base. And g must be larger than some g naught. So you can find always such a constant c and a constant c naught, g naught, such that this estimate is valid for this dimension. So what Hara and Sergi proved this way is that there's lots of cohomology, and this is completely unaccounted for in this picture. So in this unknown range, there are just many classes, sort of doubly or super exponentially many. And the stable cohomology, it does not really account for this large growth rate. So stable cohomology, so growth rate, is that the dimension of infinity is smaller than some constant, some constants to the power of the square root of k. So this is too small to actually explain this even super exponential growth. This is too small even to explain exponential growth, sub exponential, the square root of it. But it does not really account for all this growth rate. So the big question is, so what generates all this cohomology? And what's even more mysterious is that this minus sign, so for these alternating signs here, they indicate that there's also lots of cohomology in odd degree. So this has to be odd always. And to sort of illustrate how complicated this is, up to like 2 years ago, in this work of Melody Chan, Søren Galatius, and Sam Hank, there was only one odd class known. So I think this is so only odd degree class, or something like that. It was just known that that H4 of H5 of M is Z, and that was shown by Tomasi. So that was much later than this original Euler characteristic result by Haran-Zeki. And yeah, more recently there have been more also odd degree classes. But this is the story of this this mystery, and the question is what generates all this unstable cohomology. And yeah, the stable cohomology only explains a very small part. So now, very recently, this is this. 21, but the preference has been off earlier. They showed that the top weight cohomology isomorphic to the cohomology of the graph complex, of the commutative graph complex. So I don't want to spend too much time to explain all this. So this is sort of a specific part. So there's a grading on this cohomology, and we take like one the top weight part in this grading. So one we project on 1 degree. This Deligne filtration. Then there's some Poincare duality here going on. And after taking the dual, we find that this top right part is actually isomorphic to the cohomology of commutative graph. And this is the easy version of this graph. So this is also something many of you know, but this is now for me the reason to introduce this commutative graph. So how does this graph? Are there any questions?
So is there a simple reason why the even cohomology is easier to understand?
Yeah, the stable cohomology, for instance, is only an even degree. I think there are just more classes now. Also, most of the classes that come now due to this result, again, they're also strange.
Same class, homological classes, there's the first term classes. So in the sense that so anything you can write down without knowing anything.
Okay.
Is even.
Yeah, I see. Thanks.
So I will just write down the definition of this commutative graph complex. So I think most people have seen this before. So we consider pairs of the graph and an ordering on the edges of the graph. So G is a connected graph, and it has rank V, so that means it has the first Betti number G, or G loops in physics language, and it has vertex degree larger than 3, and then this ordering sigma is an ordering of the edges. And now this graph complex GCG is just the Q vector space generated by such pairs to isomorphisms and the relation. So with the relation, and the relation is that the G some permutation of the ordering is so you can always pick out the permutations of the edge labels, and you only have to account for a sign. So the edge orientation is a sign for all S for the whole symmetric group that acts on the edges. Even though it's uncommon in this business, it's always less confusing for me to just define an unusual grading, or I mean to define sort of the grading a bit differently than in many papers. So for me, I just write the C kth. So the kth graded part of the space is now just generated by the graphs with k edges. So we can just decompose this Q vector space obviously by just picking only graphs with k edges. And this is my gradient. Let's check. So this is now just graphs with k edges. Because sometimes there's a more Baroque grading here introduced, but yeah, so it's not really it. I just think that it's a bit confusing in the context of and one can see, or one can just solve the combinatorics of these graphs in this condition that the vertices should have degree at least 3, and see that and I forgot that there are also no self loops. There are no self loops. You also implement this condition. Then this has support from 0 to k. G plus 1. So this isomorphism here, if you just sort of do this little computation, you see that it directly maps like below this line, so 4g minus 6. Yeah, so actually it's yeah, sorry, I forgot to mention that that there's a sorry, forget what I said. There's another thing that I said. So, and of course there's also a differential, so otherwise it won't be a chain complex. So I still have to introduce the differential to talk about the homology of this thing. So this ck map to the ck minus 1. And the differential is just given by contracting edges of the complex. We alternate over the edges with respect to this ordering, and then for each of these, the resulting, so for each of the edges in this alternating ordering, we contract it inside the graph. And we also remove this edge from the ordering. And this way, one can just write down now. So this is now a chain complex, and we can look into the homology, which is computed by this chain complex. So just as before, I'm drawing the picture. Okay. And again, we have just some line here. Equals 3g minus 3. This is the maximum degree, which is just given by all 3 regular graphs. So there are no graphs anymore below this line that fulfill this constraint. So it's sort of the upper bound. Then there's sort of this line down here, which is this. It's g plus 1. This is, so there are no graphs below this line down here. But then there's already something like a stabilization result. So and this just says that homology groups for GCG vanish if k smaller and smaller. So there's another line here. This is a very interesting line, which is k equals 2g. Below this line, the homology vanishes. And then there's the famous result for this graph complex. Also want to mention, and this is sort of something that that is sort of that differentiates this picture here for this graph complex from the modular space of curves, because one of these lines in this graph complex picture is sort of known in a certain sense. And this is this k equals 2g line. the orange line. The orange line is just that this line is given by this only type direct sum of all this commodity group, then there's an isomorphism in this totally type relationship. This is so both these results are due to Thomas Weber. So this is already cool. So that's quite, so we know what this line here actually does in this picture. So we know at least one line, but except this line, there's also like only a big question mark. So that's also only like sporadic norm classes here. But computations are a bit easier in this picture. So there are more specific classes now above this line. So there are some computations by Barnatan, McKay, Wilbacher, and Wilbacher-Zipfowicz as well. Yeah, so some of this is also
Here, is it causing function?
yeah. On the cohomology, yeah, it's inserting graphs into each other. So you can make a lead bracket out of inserting graphs. Yeah, so you have to endow this direct sum also with the lead bracket. But yeah, and also, but I wanted to talk about to explain all this cohomology in this picture of the moduli space of curves. And there's a cool line of thought that so the problem here is that this only Teichmüller algebra is also sort of a mysterious object. So there's not that much known about it. But there's one thing known due to Francis that there's an injection of a 3D algebra. So there's a 3D algebra living in there. And we know what the generators of the 3D algebra are, and we also know that it has like infinite generators. So we really know that there are many classes here on this line, thanks to this theorem. And by this isomorphism, we also know now that there are many classes in here. So this now that's another, unfortunately. Yep, this moves to this goes to the so this interesting line goes right below this upper limit. So this is for the 6 and equals k. This line is where this GRT1 maps to. It does not explain the complete cohomology in this line, but this top weight degree piece. So there's now one line that is at least partially known. So that's the cool stuff there. And it also explains like exponential growth rate for this line. So from this result, it follows that the dimension of these homology groups, it's growing more than exponentially, or it's growing exponentially, not more than exponentially. So there's some constant c and some for large enough g, this has like this exponential. Okay.
Sorry, is the free algebra in common unit?
In they're graded. They are always in odd degree, except for one. There's no generation for one. Then degree Okay. So now, so this brings me now to the actual talk with this motivation, and yeah, so maybe let me reiterate. So this whole picture, this map of this GC2 graph complex, it now maps to this picture for the homology of modular space of curves, and it starts sort of with the interesting part down here, up here, and it's Poincaré dual, so it goes like from top to bottom, and there's sort of a new auxiliary line where this isomorphism does not really bring you any new information, and this is exactly the middle of this homology. And in this region, we at least know that there's this GC, there's this commutative graph complex living in this top view. And so we have all these classes coming back from this commutative graph complex, and the aim now, or the rest of the talk is now about estimating the amount of homology that is in this GC2 complex in this unknown region here via an Euler characteristic island. So and of course, this also means that some part of the cohomology of MG is concentrated right in this. So the question is how much of the cohomology is living like in this top degree piece here. So can of course just compute the Euler characteristic of this commutative graph complex. Just the dimension, the alternating sum over the dimensions with the Betti numbers. And this computation has an interesting history. So there are different formulas. There are quite many different formulas for this Euler characteristic, actually. So there's one, so at least there are many already that I'm aware of, maybe there are more. So there's one by Euler and 2015, I think. And then there's one that uses completely different methods by Sotomina. That yields a completely different formula, and also works in a bit of a different context. So they're also complementary, these kind of formulas. It's one by Chan, Galashis, Faber.
Could you write a little bigger, Michi?
Yes, I can try. There's very little space on this blackboard, unfortunately.
Yeah, sorry.
That's from 19, I think. And all these three formulas, they're not really suitable to extract the asymptotics of this value, unfortunately. So, all not suitable for asymptotics. So these formulas, they can be used to compute the Euler characteristic for a couple of values of G, but it's difficult to extract the asymptotics. So that was 4 So that's my computation. So that's also motivated. So I computed this Euler characteristic again due to also a talk by Francis in 2020, where he made the conjecture that certain forms, actually, or not really the conjecture, but he implicitly conjectured perhaps that certain forms generate this homology here of this commutative graph complex. There's another computation now, and the fun thing was that all these formulas are completely different. And to me, it was unclear how they are actually related at first. And also, I have to say that this Chan-Faber-Glacius pain formula is more general because it also allows for graphs with legs. So you also have something more complicated. Here, you actually have only graphs with legs allowed. And here's the sort of legless case discussed, but also for other types of graph complex, not only the commutative graph complex. So all these formulas, they have some features, different features. But this was computed with the aim of extracting the asymptotics of these numbers for large G to get an estimate of the amount of homology in this unknown regime. Eventually, so I found also this paper by Chan-Faber-Glacius, they used a formula and proved it that was conjectured by Zagier in sort of some unpublished notes. And this year, I finally got a hand on these notes, and I figured out that in these notes, Zagier, and this is unpublished or private notes actually. So I met Zagier, and I was able to find them. And he actually conjectured this formula in 2008 already, and didn't prove it, but he conjectured 3, but proved that 4 follows from 3. So that sort of closed this gap. So these unpublished notes, and this number 4. There you can also, I mean, it's still some work to do to extract these asymptotics, but you can prove a formula for this. And yeah, so the result is this is the new result. Only thing, no. That this Euler characteristic of this, it's behaving also very oscillating or alternating. Like the formula. Yeah, this is probably too small, right, for Zoom.
Yes, it's too small.
Even for what? Even for ear. Okay. So I need more space. There's some water or something.
So it's your new theorem. You should make it big enough so we can see it.
Yes, I'm aware of that. So this is this sufficient, or can you read this now? Or is it still too small? Okay.
Yes.
So there are 2 cases. The first case is minus 1 be over 2. So you can always already see that G is supposed to be even here. And that's -2. And that is for large even G. And then the odd case is more complicated. There's a prefactor, and then there's a strange function. And then we have this function is given by sine of unfortunately a bit technical. So there's this. So this is for odd, for large odd. So there are two cases for G: the odd and the even G's, and you have a different asymptotic behavior for the odd and the even ones. For the even G's, it's a bit simpler. You have sort of a factorial growth rate here. You have this alternating sign again that now, of course, alternates like in steps of 4. So there's a different alternation than in the original modular space. And still here you have, of course, the super exponential growth rate for large odd G, you have this strange prefactor which is heavily oscillating. So there's lots of oscillations. So there's lots of negative numbers in this Euler characteristic for large G, and still you have some asymptotic behavior which is governed by an exponential function and factorial. So still, for both cases, you have super exponential growth rate in the Euler characteristic. So from this it follows that there's lots of cohomology in this top weight degree rated piece of the modular space of curves. So to express it explicitly, I have to write large enough to read it. So if you sum over all this green part, so this part where this isomorphism actually makes sense and has support, where we can map this commutative graph complex into our cohomology of the modular space of curves. This is resulted by Chan, Delicious, and Payne. There we can look into, we can sum over all these degrees, all the interesting degrees, and we can estimate the dimension of this top weight graded piece from below. And we see that there's super exponentially much cohomology in there. We can find a constant C, and for sufficiently large G, that this grows super exponentially. But you see that in contrast to the Harasagi result, there's only like a single G in the exponent here. So where Harasagi had like the double factorial, so the G to the power of 2G, we only have like G to the power of G here. So there's still lots of cohomology missing. So it's not concentrated in this top weight degree graded piece. In fact, it's also in So this also we don't know if it could also be concentrated there, but it does not explain this large growth rate of the Euler characteristic of the initial Hara-Zagier formula completely, but it provides at least sort of a subpiece which also grows superfactorial and super exponential. Okay. So how much time do I still have?
15 minutes.
So that's the results, and for the rest of the talk, I will briefly talk about the proof and the formulas that pop up. If there are no questions. Also,
so it's, am I reading this right? That so the growth rate is faster in odd degree than in even degree, but both of them are somehow in between exponential and factorial?
Right. So so that's not the degree, that is the genus.
Sorry, yeah, yes,
Yeah.
yes.
So, but yes, exactly. So that's both factorial. But you have this lower growth rate down here than here. G over 2. Yes. All right. Sorry. Actually, it's also this 2 actually survives down here. Yeah. So you have a normal G for the even case, and you have a G over 2 for the odd case. Yeah. So in general, it's only like G over 2. Because there's this G over 2 factorial.
But Michael, are you saying that? Wait, what am I reading wrong here? So to me, it looks like odd G is growing faster in absolute value, right? That on top you have a pi to the minus G, and on top you have a pi to the minus G over 2.
Yeah, no. Eventually, G over 2 factorial. It's much smaller than G factorial.
I see. Okay, that's sorry. Okay.
Everything else. So this is just so eventually it's just going to be a battle of this and this term.
Oh, okay. Thank you. Thanks. Okay, that's what I was missing. Got it.
And this is also this G over 2 is also responsible then for this G over 2 up here.
Okay. Okay. Thank you.
But it's all super exponential. That's the so,
yeah. Okay. Super exponential and subfactorial.
Right. I mean, it's factorial with a half argument. So, and it's factorial in the even for even G, and it's for odd G, it's sort of half factorial. So versus Hara-Zagier, where it's sort of doubled in the argument. So,
okay.
So this is there's sort of a hierarchy going on here.
Okay, thanks.
Okay. So, like I said, I'm only going to say some words to this formula and to the proof. So there are many, obviously, also from this from the many formulas for Euler characteristic. There are many ways to prove this. The most straightforward way to prove such a formula is to use a work by Gessler and Capano. Use their results from 98, I think, and so there's a theory how to actually compute these Euler characteristics. You can use this theory also to estimate or to compute this Euler characteristic of the commutative graph complex. But this is a bit complicated to use this theory. So there's a simpler combinatorial way in combinatorics, and it boils down to the same thing essentially. So what you do, of course, is you count the dimensions of this of the kth degree graded piece, and we know that the Euler characteristic it's just equal also to the alternating sum over the dimensions of these vector spaces. It's independent of the way we set up this complex. Okay, so the trick of the proof, I'm not going to have time to discuss this in detail, but the trick is to count graphs or to count tuples of set of half edges, set of edges, vertices, and a permutation of the half edges, and you interpret this triple of half edges, edges, and vertices as a graph. And this permutation, it has to be compatible with the graph. This permutation, so this is from the half edges to themselves, and you interpret this as an automorphism. Of the graph. So let's say this is G, and we just interpret, so we count a pair of a graph with an automorphism, and then we can calculate the number of generators in each degree, which are just graphs, which are just isomorphism classes of graphs. And this is equivalent to count graphs with a coloring on the half edges. So we have this way we have tuples of half edges, edges, and vertices, and some eta which actually just maps our half edges to the positive integers. And these half edges, these colored half edges, they now correspond to the size of the cycles of this computation. So you shrink all cycles in this automorphism to a single half edge, and this way you can count these kind of tuples. Of course, you need to have some conditions on these objects to make this counting work properly, and you also have to account for this sign issue with this relation on the sign of the odd and even automorphism of the graphs. This is very sketchy, but I don't have time to make it super detailed. I just wanted to flash some of the ideas. This idea also had another application where Karen and I, this is work in progress, where we computed the asymptotics of the Euler characteristic of out of n, which is another space that can be described or whose cohomology. Yeah, this is a group, the automorphism of the free group, and we can understand the group cohomology by another graph complex. And we also computed the asymptotic growth rate of this Euler characteristic. which you can compute by using similar methods and also similar counting techniques. Eventually, this counting problem, and there it does not really matter anymore if you start from this Gessler-Karpanoff approach, or you just follow the combinatorics. Eventually, you can write this down nicely as a formal quantum field theory expression. So you can define quantum field theory potential, which looks a bit strange. Some stuff here's all the variables y, k. We take these. So this is a sort of a formal expression and infinitely many variables. These are indexed by y's, y1 to 1, y1, y2, y3, and so on. We take here always the variable with index k times j. And okay. And then we divide the whole thing by 1. And then also 2. So this is now sort of this potential for zero quantum field theory. This is very technical. I apologize, but I wanted to illustrate this a bit. But this is only this is a correction term you need for these even respectively automorphisms, and this is a sort of a power series in y1, y2, y3, and so on, and also z to the power 1/2. Z is Z inverse is sort of the Planck constant in this quantum field theory from the perspective of mathematics. It's just a marking parameter that counts the Euler characteristic, and the expression that you eventually get is just a formal infinite dimensional integral. We take the product of all these yk variables, normalize it such that we can compute Gaussian integrals. We have this infinite dimensional Gaussian integral, and its integrand is given by a sum over all these j expressions. And the theorem is now that this is now equal to and this size so this psi encodes this Euler characteristic which we actually want to calculate, and this is sort of a quantum field theory object that computes this Euler characteristic. So it's an infinitely many parameters, so infinitely many fields, but they are all sort of zero dimensional. So in the way we can think about it as sort of a quantum mechanics integral that computes this order characteristic. Yeah, so that was just for sort of motivation also from the perspective of physics, because we're here sort of also discussing like physics and finite integrals. I hope it was not too technical for mathematicians watching. Yeah, so interesting is that this original Gessler-Kapranov computation was for a different graph complex that computed also such an order characteristic. For the so they computed the associative graph complex. And they get a related formula for this psi. And yeah, so there the methods work similarly. And do I still have time, or maybe 1 minute? I mean, if I want, if you insist, I can still write down the equation for this generating function now. But yeah, so I can just quickly write down the equation. So if you evaluate this integral now, so you can evaluate this thing just explicitly or relatively explicitly to get the following expression. This is the final one. So this follows from this is that this generating function here. You can take this logarithm, and then you get an expression that also again sums to the j. And this is so this expression out here is then eventually the one that is accessible for asymptotic computations. Accessible way. There are these two functions b and a, and they are pretty simple things. B is just the Bernoulli numbers, essentially, or the generating function of the Bernoulli numbers. And A is essentially just some logarithm. And oh, what I forgot. Sj is these polynomials that are encoded by the Möbius function. These are these cyclotomic polynomials. So these are certain polynomials that are given by the Möbius function, and this formula, this very complicated looking, or still quite complicated formula, fortunately now accessible to asymptotic methods. And you still have to work quite hard to squeeze out asymptotics from this, but it's possible. And yeah, what I wanted to mention, so what is mysterious to me, and I would like to understand, is that there's this associative graph complex, and Gessler and Kapranov, they computed the same expressions of also the Euler characteristic for this associative graph complex that has also something to do with the modular space of curves. And they get the same formula, except that this mu here, this Möbius function, is replaced by the torsion function, the Euler. Yes, so that's it. Sorry.
Thank you. Other questions? Maybe do it alternating. Start with the audience here. And people online.
Can I ask a question?
Yep.
Sure.
Hi, Michi. I'm sorry I'm not there. I hope I can make it later this week. So in principle, for your calculation, so you wanted to compute something about the Euler characteristic of the cohomology, right? Or homology. So I guess the 0th step in your calculation is that you replace the alternating sum of the dimensions of the homology groups, but just the alternating sums of the dimensions of the vector spaces given by all graphs. Is this correct?
Yes, I was. Yeah, I only went through this very briefly. I'm sorry. Yeah.
Okay, so my question is, so what you're doing is you're summing over all the graphs.
Yeah.
With some very specific weight, so to say, for every graph that counts you these alternating dimensions.
Exactly.
Now, in physics, there's all these toy models, right? So I was wondering, potentially you could consider other sums over all the graphs with slightly different factors for every graph. I don't know. You know, there's different games you can play, different kind of Feynman rules you can apply to every graph.
Yes.
So I was just wondering, have you ever thought if any of these other sums of graphs could have any connection with cohomology or homology?
Well, I mean, there are quite a couple of. So this is sort of this quantum field theory, and this Vj, it just encodes you the Feynman rules. So this is just an encoding of certain Feynman rules on this sum over all graphs. And yeah, so this is a specific potential, but you can also use, for instance, the potential for this associative graph complex.
Mm-hmm.
It also gives you such a formula. Yeah, I think so there are, of course, infinitely many possibilities to just assign some Feynman rules to graphs. Or some map, but yeah, it's more. So yeah, I think more about the other direction. So if you have something interesting to compute, how do you figure out the Feynman rules that actually compute you the interesting variance? So,
yeah, I guess I'm suggesting you can try to go the other way. I mean, if you have a good pool, I mean, the thing is, you will have to use some particularly nice form of these V's, right, to be able to compute anything in a nice form.
The new thing there is that here you really have these infinite dimensional integrals. So so it's still sort of countably infinite. It's from the perspective of quantum field theory, it's very, very tame still to have like only an integral over a countably infinite dimensional space. So you integrate over all these variables, and there are infinitely many of them. And you have a Gaussian kernel, so there's a Gaussian thing in here. So there's a normal propagator and everything. Yeah, so this is not so common to actually solve these computational problems on this level of complexity already. I mean, there's of course also the Chern-Simons integrals, but they Chern-Simon theories and so on, but they don't sort of work in a different manner or a different kind of idea behind them. And yeah, what might here be interesting to actually interpret it somehow as a more physical system, because there's infinitely many degrees of freedom. And you could sort of ask the question, can I write down, yeah, what kind of physical system has these infinitely many degrees of freedom? Can be a quantum mechanical system, for instance. So can you sort of write down a one-dimensional system that has exactly this, that is somehow living on some compactly supported space that has exactly this kind of.
Okay, but at the moment it's not clear how to go beyond the Euler characteristic if the question is about homology.
Yes. Yeah. No, this is really like tailored only for counting the graphs.
Thanks.
So maybe related, can you incorporate legs to the story?
Yes.
Because when you talked about these coloring half edges,
Yeah.
it seemed that, I mean, legs are just half edges that are not paired.
Yes.
Can you make that work?
Yeah, in fact, I mean, this was just sort of the case without legs, but these different formulas that exist, also the conjectured formula by Zagier, proven by Champa relation, it involves like the Euler characteristic for graphs with arbitrary many legs. And yeah, one can also make this analysis, but probably one can make it. I didn't do it, but it's probably also more complicated. So maybe there's a simpler argument where one can just relate the different moduli spaces, because you can also just forget the punctures.
I have a very quick second question, if I may. If nobody else has a question on. Okay. So when one computes the cohomology or homology of the graph complex, like one of the first steps is that you reduce to vertices is valently bigger than or equal to 3 and connected graphs. So it's like these preliminary steps, right, to reduce it, and then you get GRT in H0. So my question is, in physics, you have this analog steps, right? You have the connected, the 1pi, the different kind of Green's functions. So I was just wondering if this is the direct analogy or if this is the superficial analogy. So in other words, if you were to do the whole thing also for disconnected graphs, or if you would lift the valency lower bound on 3 on the vertices, and you would do the same thing, would you then also reproduce the kind of algebra structure of the graph complex with these fewer constraints?
So if you have fewer constraints on the, sorry, I didn't really.
Well, I mean, you have this. You can count just these. I guess you're restricting yourselves to connected graphs here, or not?
Yes, but if you do disconnected graphs, then there's the homology of this complex is then also pretty trivial to compute. In fact, I mean, what this does, it actually computes the Euler characteristic for the disconnected case, and then you just sort of compute this. So this psi is the connected case.
Yeah.
And this exponent together. So this is called the Polya exponential. This this weird exponentiation of this psi generating function.
Mm-hmm.
And this just translates in this context of isomorphism paths from disconnected to connected.
Okay, so you're using this logarithm to get to the connected part piece from the beginning. Okay, thanks. That answers my question.
Can I ask a question?
Yes.
Is it possible for you to comment at all on orbifold versus ordinary Euler characteristics, and maybe inform me a little bit? Like, I feel like maybe at some earlier point, I naively thought that these were supposed to be asymptotically the same, and then squinting at some of your work, I learned that wasn't the case. Maybe you could comment.
Yes, so you can also compute this orbifold Euler characteristic, and there's sort of so this is maybe a conjecture, but yeah. So in this original paper by Kontsevich, he writes that you expect that the rational Euler, so this orbifold Euler characteristic, is expected to be equal to the classic Euler characteristic in this kind of context. But yeah, there's no reason I know of to actually believe this, except for the fact that these torsion groups, they are expected to be small. So if you think about it from the perspective of computing the Euler characteristic of the group. But also, I mean, you can just see it that the orbifold Euler characteristic of this graph complex, it's given by just the Bernoulli numbers actually, and these are vanishing or all odd or even, I don't know now, but there's definitely like lots of values where this vanishes then, this orbifold Euler characteristic. So, and this is, so the point where it vanishes, it's also where this equation, this asymptotic equation that I had before is interesting. So where this weird behavior pops up. So yeah, this shows that they are not equivalent asymptotically because they are maximally different. The rational one is vanishing, and the orbifold Euler characteristic is vanishing, and the classic one is actually quite large. And the same phenomenon also appears like for this Euler characteristic of out of n, but in a different way. So there's just a different factor. So the classic Euler characteristic is equal to the rational, so the orbifold Euler characteristic up to a finite factor. That's just the quotient is converging to a finite number or large. Does that answer your question?
Yes, thank you.
So you might point out that we know that number
Yeah, it's
for out of Fn.
yes, I wrote it down briefly, but yeah, it's so for out of n we have high out of n, or the other way around. So this classic Euler characteristic divided by orbifold Euler characteristic. If you take the limit n to infinity, then this is equal to e to the power minus 1 over 4.
So are there situations where you might guess that this kind of behavior holds, like you know, some relationship between the two Euler characteristics? Or
yeah, it's indicated. It's so the orbifold Euler characteristic. It always sort of comes from the graphs without. So we just forget that all graphs have automorphisms. So of course you can also say that there's this. So in graph theory, it's also known that almost all graphs have no automorphisms, and this is true. But here in this case, for this commutative graph complex, we have to sum over a very alternating sum of graphs. So the number of edges, this produces a heavily alternating sum, and there are so many cancellations. So this growth rate of this alternating sum is much smaller than the total number of graphs. So so this intuition, it does not have that much anymore, but it's eventually it's still a bit true, because for the odd case, for the odd G, the rational and the integral Euler characteristic are also equivalent. So for odd G, the classical Euler characteristic is indeed just equal to the, at least asymptotically, it's equal to the orbifold Euler characteristic. But of course, for the other case, where the orbifold Euler characteristic vanishes, you also get a large growth rate.
thank you.
But yeah, I don't know of a reason a priori why to believe that these numbers should be the same or asymptotically the same, up to this intuition that the torsion groups are thought to be small.
For the physical interpretation, what can help is to realize that the yk, the modes of conversion to field of this.
Exactly, yeah.
And in fact, I mean, the only place where I know there's an exponential in the action theory.
So could you repeat the question, please? We couldn't hear it.
Well, it was more to remark that in order to try to get a physical interpretation of this particular action, one can try to realize the yk as the modes of the field in the disk, the Fourier modes. And there's one case well-known case where there's an exponential interaction, like the dj is already itself an exponential. It's in Euler theory. You take the Gaussian free field, and then you buy the measure by, again, exponential the Gaussian free field.
Okay. Yeah, that looks very promising. I will have to look at it.
I don't think that particle is Euler because it becomes a particle wave.
Yeah, so we can, yeah, the idea would be really to just interpret all these things here as modes of something, like maybe on a torus on this or something.
Okay.
So you say that for the associative graph complex, then you don't have this function, you would have the Euler Tolkien function.
Exactly, yeah.
And so I mean, the relation between Möbius and Euler Tolkien, I think you can go by look at the divisibility process. And yeah, that might be whatever inverse from each other.
I mean,
So I wonder if there's some actually combinatorial directly available of the graphs.
Yeah.
You can build some graph from the other by generating series by using a certain process.
I mean, I have to mention that there, so between this associative and commutative graph complex, there are all kinds of relations. So there's a whole, but yeah, I don't know which one might explain this sort of symmetry between these two formulas. So there's also this, well, we are not Cousin dual, but there's another duality.
Okay, Ralph.
Yeah, so anyway, actually one covers the other, that's probably, and then also might explain this thing. So, but maybe this is too long. There was a giant leap in your thing where you were counting graphs and then you wrote the formula. So it wasn't, so
Yeah,
I believe that, but maybe that takes too long to explain what was going on. But first you were counting, and then maybe just for the count you had before, so you had the graph, right? And then you were counting the automorphisms of the graph as well. So what
yes.
I didn't see what you were counting. So you were you're not dividing out by the automorphisms, right?
Yes, I divide out by the automorphisms automatically, unfortunately, because usually with these kind of methods, with these kind of PTU methods, you always divide by the automorphism. So,
but then you had pairs where you were keeping track of the automorphisms. So
exactly.
It wasn't clear to me how you divide it by keeping track of it.
Yeah, you do both.
Yeah, okay.
You multiply and
You divide by the square.
yeah, so I was very fast there because I wanted to take sort of the time for this very lengthy introduction. So,
I'll tell you why, because I mean, in the paper we just put this thing inspired there. These things, they look very close to the slice categories we have. Just write down what the complexes are to do a W construction on. So these combinatorial things you write down have a meaning.
okay,
As morphisms of some graphs.
I see.
And so, but it wasn't so. But then instead of dividing up by the morphisms, you're adding something. So go ahead. I mean, that's why.
Yeah, I know. So these are these groupoids. No, do you mean this?
It's like a Guzzo's category. Like somehow size category, Guzzo's category.
Okay. Yeah. So I mean, maybe
We
we can
say
discuss
that.
this. Some of the techniques a bit. So if you have more questions on the computation, I can also just explain it in more detail. But yeah, you see, I only like flashed through some technical parts of it. It's a bit, so there are quite some technical steps that are omitted. Yeah. Sorry.
Okay, then let's thank Michi again.